Good morning, everyone. My name is Wang Chi from University of Witwatersrand, South Africa. And it gives me great pleasure to host this morning's session. And our first speaker this morning is Professor Jan Harm van der Walt. I hope I pronounce your name correctly, from University of Pretoria, sunny South Africa. He will be giving a talk on convergence structures on vector lattices. Jan, please start. Thank you.
Thank you, Wenchi. And first, let me thank the organizers for giving me this opportunity to share the work with you. So this is a joint work with Yuri Conradi, Michael O'Brien, and Vladimir Troitsky. So my talk is kind of educational in a way. I will be first giving a motivation from the point of view of people working in vector lattices for why we should consider convergence structures. Then I'll speak about nets and filters. And then finally, I'll talk about convergence structures. And here I will first discuss how to formulate this concept in terms of filters. And then our contribution here is to show how this can be done in terms of nets. And then I will give a few motivating examples and an application if time permits. So before I answer the question why convergence structures, let me first say what is a convergence structure, very loosely speaking. A convergence structure is a generalization of a topology in which the primitive concept is not that of an open set, but that of a convergent net or a convergent filter. Right. So why convergent structures? Well, from the point of view of vector lattices, let us look at the following definition, which most of us will know. A net, and that is the definition of order convergence. Right, so net V alpha, order converges to V in a vector lattice E if there is a decreasing net U beta, which dominates modulus V minus V alpha in this way. And it is well known that in general there is no topology on a vector lattice E, so that order convergence in E coincides with convergence with respect to this topology. So we will say that order convergence is in general not topological. And so here is a brief example, which I'll quickly go through. So let's look at the vector lattice of continuous functions on the unit interval C01, and let's suppose that order convergence in C01 were topological. So there is some topology on C01, which gives you precisely the order convergent nets. Right, so we're going to create a net and derive a contradiction from this. So we enumerate the rational numbers in the unit interval in such a way that every cofinite set is dense in 0, 1, and we let our index set be n squared, so pairs of natural numbers. And now we define the following function for a pair of natural numbers, alpha equals mn. We have this tent function. So let me just briefly draw a sketch. Right? If there is Qn, then we make a little tent function like that. Right? So minus 1 over n and plus 1 over n. Right? So now what happens is this tent function grows narrower as m goes to infinity, and it moves around the unit interval. So because of this, the way we've enumerated the rational numbers, so that any cofinite subset of them is dense in the unit interval, the supremum of U alpha for alpha bigger or equal to alpha 0 is always the constant 1 function, and therefore this net does not order converge to 0. Now, because we're assuming that order convergence is topological, there's a neighborhood V of the constant 0 function and a subnet, which I've written U alpha beta of U alpha, which is never in V. But this subnet has a further subnet which converges in order to 0 and must therefore eventually enter the neighborhood V, and that gives us our contradiction. And how we know that this convergent subnet exists is because we can select from the U betas a further subnet so that the corresponding QNs converge to some real number. And then this subnet of the U betas will converge in order to 0. And so that's one example. Recently, those vector lattices for which there is a topology inducing order convergence of nets was characterized. These are precisely the finite dimensional vector lattices. So in almost all interesting vector lattices, order convergence is not topological. So if we want a kind of general framework in which to discuss order convergence, one must look beyond topological spaces. Now, the second very familiar notion of convergence in a vector lattice is that of relatively uniform convergence. Right, so V alpha converges relatively uniformly to V if modulus V minus V alpha is dominated by epsilon times some fixed positive U for alpha sufficiently large. And again, there is in general no topology on a vector lattice E, so that relatively uniform convergence in E coincides with convergence with respect to this topology. At another quick example, let's look at C00, so the space of finitely supported sequences of real numbers. And relatively uniform convergence on this space is not topological. Right? So let's again suppose that it were topological, and we now construct a sequence indexed by pairs of natural numbers in this way. So this would be, so UNM would be the sequence in C00 with the first n terms equals 1 over m and all other terms equal to 0. So for each fixed n, if we let m go to infinity, then UNM goes to 0 relatively uniformly in C00. Right? And now we're going to create a new net. And so we make our index set, the natural numbers cross sequences of natural numbers, everything ordered component-wise. And for an alpha, which is now a natural number n and a sequence jk of natural numbers, right, we let V alpha be UNJN. Right, so for instance, if alpha were, let's say, 2, and now here we have the sequence, let's say, 3, 5, 7, and so on, then V alpha would be U2, and from the sequence U2M, we now select the fifth entry, like so. Okay. Now, because the relatively uniform convergence on C00 is assumed to be topological, this net will converge to 0 relatively uniformly in C00. And that's a little generalization of this classical diagonal property for convergent sequences, say in a metric space. But if you look at the sequence of the sequence V alpha, we'll see that every tail of this net is unbounded in C00. Right? Because the supports of the V alphas sort of increase. And so we have a contradiction. So again, relatively uniform convergence is also in general not topological. So now we can ask, can we give a characterization for those vector lattices for which relatively uniform convergence is topological? Similar to the characterization that exists for the convergence. So here is a theorem. So we can, in fact, characterize those vector lattices for which relatively uniform convergence is topological. These are precisely the vector lattices for which which contain a strong order unit. And so if you have a well, I think it's the other direction. Right? If E contains a strong order unit, then a relatively uniform convergence is, in fact, norm convergence with respect to the Gauss norm generated by the order unit. Right? So in that case, relatively uniform convergence is certainly topological. So let's look in the other direction. So let's suppose E has no strong order unit, but RU convergence is topological. And now you may notice that our argument will be just an abstraction of what we've done before for C00. And so because we have no strong order unit, for every positive and non-zero U, there is an F sub U, also positive and non-zero, so that Fn is, Fu is not dominated by Nu for every natural number n. Right, so these F sub U's can be chosen to be increasing. Right, so now we make a sequence F sub Un being 1 over n F sub U. And this certainly converges to 0 relatively uniformly in E for every U. Right, and now we do a similar trick to what we did before. We make an index set I, which is a non-zero positive elements of U of E cross functions from the non-zero positive elements of E into the natural numbers, ordered component-wise, and we define our sequence G alpha in a similar way to what we've done before. Right? We make this kind of diagonal net. Right? And again, because we're assuming relatively uniform convergence on this space is topological, this sequence will converge, this net will converge to 0. And this will again give us a contradiction. Okay. So relatively uniform convergence is topological if and only if E has a strong order unit. Right. So again, we see that there are plenty of very interesting vector lattices for which relatively uniform convergence is not topological. Right. So let's talk about nets and filters. Right. So I'm going to look at the definition of a net, and I'm doing this because it turns out that there are non-equivalent definitions for nets and subnets in the literature, and I want to be very clear exactly what I mean by a net and a subnet. Right? So a directed set is a pre-ordered set so that any two members of the set have a common descendant. A net in a set X is indexed by a directed set I is a function X from I into the set X, and we will usually write it in the normal way, X sub alpha, omitting the index set when this is not a cause for confusion. We denote the set of all terms in the net as such, and for all alpha 0 and I, we look at the net indexed by alpha 0 bigger or equal by alpha bigger or equal to alpha 0, and we call this a tail of the original net. The range of this new net is called a tail set of the net, and we denote by x alpha in triangular brackets the set of all tail sets of the net. So just some notation. Right. So let's look at subnets quickly. So we are following Kelly's definition of a subnet, which is the most general, well, second most general. Right, so Y beta is a subnet of X alpha if there's a function from J into I, so that for every alpha, there's a beta alpha in J, so that phi of beta is bigger or equal to alpha for all beta bigger or equal to beta alpha, and Y beta is X of phi. of phi beta for every beta in J. Right? And now something which is less familiar is the concept of a quasi-subnet. So Y beta is a quasi-subnet of X alpha, which we write in this way. If every tail of X alpha contains a tail of Y beta as a subset. Right, so note that the particular ordering is not so important on the index sets, is not so important here. It is just the relation between the tail sets of the nets that matter. We say that two nets are tail equivalent if either one is a quasi-subnet of the other. And we use this equivalence symbol to denote this. So clearly every subnet of a net is a quasi-subnet, but not conversely. Okay, let's talk about filters. So a filter base on a non-empty set X is a non-empty collection B of subsets of X, which is downward direction with, which is upwards directed with respect to reverse inclusion. So in other words, if A and B are in the filter base, then there's a C in the filter base, which is contained in their intersection. And a filter is a filter base which is closed undertaking supersets. A very simple example of a filter is the principal ultrafilter generated by a point X in your space, which consists of all subsets of X which contain the point X as an element. Another example is the neighborhood filter at a point in a topological space, right, which consists of all sets that contain X in their interior. So the key to coming up with a formulation or an axiomatization for a convergence structure in terms of nets is to understand the relationship between nets and filters, right? So how do we move from nets to filters and vice versa? So let's first talk about going from nets to filters. So we have two nets in a set X, X alpha and Y beta. If we look at the collection of tail sets of our net, say X alpha, then this is clearly a filter base. And the filter generated by this filter base we call the tail filter of X alpha and denoted by square brackets X alpha. And this consists of all subsets of X which contain a tail of the net, or a tail set of the net. It's not difficult to see that if Y beta is a quasi-subnet of X alpha, this happens if and only if the tail filter of X alpha is contained in the tail filter of Y beta. And X alpha and Y beta are therefore tail equivalent if and only if they have the same tail filters. Right, so if we have a topological space and a point X in X and two nets X alpha and Y beta in X, then X alpha converges to X if and only if the neighborhood filter at X is contained in the tail filter of X alpha. And if X alpha converges to X and X alpha is tail equivalent to Y beta, then Y beta also converges to X. So this tells us that convergence is a tail property. Right? So the actual ordering on the index set doesn't matter. It is only the tail behavior of the net that determines its convergence properties. Okay. So this is how we go from nets to filters. How do we go back? So let's take a filter on a set X, and we're going to create a net whose tail filter is equal to F. So we take as our index set pairs Fx, where X is an element of F and F is in our filter, and we order it by looking at reverse inclusion on the first component, so on the set in the filter, and if we have such a pair alpha equals fx, then we set x alpha equal to x. And then this is a net in x, and its filter of tails is precisely the original filter f. So if x is a topological space, and we take a point in x, then we say that the filter f converges to x if this if this net that we've associated with the filter f converges to x. And that means that the neighborhood filter at x is contained in our filter f. Okay, so this is what we need to know about nets and filters. Let's look at convergence spaces. So there are several non-equivalent concepts in the literature which are all called convergence spaces. And so we are going to use the following one. A convergent structure on a set X is a mapping lambda from X into the set of filters on X, so that for every X in X, the principal ultra filter belongs to lambda X. If F is in lambda X and F is contained in G, then G is in lambda X. And if F and G belong to lambda X, then F intersect G belong to lambda X. And we think of F belonging to lambda X as F converging to X. And we will write it as such. So we can, following our discussion earlier, we can define the convergence of a net in a convergence structure by saying the net converges to X if its filter of tails converges to X. And every filter on X is actually the tail filter of a net on X. So this tells us that we should be able to axiomatize a convergence structure in terms of nets. And this is what we're going to do now. So this is part of the folklore in the theory of convergence spaces, but it is never explicitly shown how this can be done. So let's look at the first axiom, right? So if we have a net in X, then its filter of tails will be the principal ultra filter at X, if and only if this net is eventually equal to X. So if we want to replace this first axiom of the definition of a convergence structure with a net equivalent, we should say that if X alpha is eventually equal to X, then X alpha converges to X. And we can actually make this a bit simpler by just looking at actual constant nets. So any constant net with all terms equal to X must converge to X. And so this is the net equivalent of the first axiom of a convergence structure. Let's look at the second. If you have two nets, X alpha and Y beta, then Y beta is a quasi-subnet of X alpha if and only if X alpha, the tail filter of the X alphas is contained in the tail filter of Y beta. So the net equivalent of this monotonicity axiom in the definition of a convergence structure can be formulated as if X alpha converges to X and Y beta is a quasi-subnet of X alpha, then Y beta converges to X. So if you would prefer to stick to classical subnets instead of quasi-subnets, then you can replace this with the following two conditions. A subnet of a convergent net is convergent, and if X alpha converges to X and is tail equivalent to Y beta, then Y beta converges to X. Right, so this second condition here is already captured in the one formulation we have above. Okay, now let's look at the last one, and here this is the one which is a bit more difficult. So we need to find a way, because now we're talking about the intersection of two filters. So we need to find a way of combining two nets, and here is one such way. So if you have two nets, X alpha and Y beta, then we look at the index set K, which consists of tuples alpha, beta, and Z, where alpha is in I, beta in J, and Z is either equal to X alpha or Y beta. And if we have such a tuple gamma, then we set Z gamma equals to Z. and the resulting net we call the mixing of these two nets, X alpha and Y beta. And we can show that if we look at the intersection of the tail filter of X alpha with the tail filter of Y beta, then this gives you the tail filter of Z gamma. So then clearly we can replace the filter axiom, which says that if F and G both converge to X, then their intersection converges to X. We can replace this with the axiom that if X alpha converges to X and, oh, that's a mistake, Y beta converges to X, then their mixing also converge to X. And so another way of formulating this, so again, we have an alternative formulation, is to say that if X alpha converges to X and Y alpha converges to X, and you have another net Z alpha, so that each Z alpha is either X alpha or Y alpha, then the net Z alpha converges to X. So this is an alternative way of formulating this, this condition. Right. Okay, so we can now formulate the following net definition of a convergence structure. So let me get them all up here, which is just those conditions which I've just discussed. So something to notice here is that we have to use a class, right? A proper class. And that is because no matter which non-empty set you take, the set of all nets, well, the collection of all nets in that set is not a set, it's a proper class. So one way of getting away from this is to restrict yourself to nets indexed by specific index sets. So this is what we're going to do here. So we take X a set, and then we construct these VNs here. And those of you familiar with non-standard analysis will recognize this as the superstructure of X. Right, so a net X alpha is admissible if the index set belongs to one of these VNs we've defined here. And every net in X is tail equivalent to an admissible net. So you have an arbitrary net, you can, for the purposes of looking at convergence, you can replace it with a net that is indexed by a set from the superstructure. And the important thing is that the collection of admissible nets in X is a set. And so if we restrict ourselves to admissible nets, which we can to some extent due to this proposition, then we can give a net definition which is in ZFC. Right, so the axioms is the constant nets converge. If a net converges, then so does each of its quasi-subnets, which of course we can formulate alternatively by using ordinary subnets. And so if a net converges, then every subnet converges, and then if a net converges, then and another net is tail equivalent to it, then the second net also converges, and then of course this last mixing condition. Right. So this is a partial circumvention of having to use a proper class. One cannot entirely get away from working with nets that are not admissible, because you want to talk about functions between different convergence spaces, and then this results in problems. Okay, so let me just end with.
Sorry, Jan, you have 1 minute left.
Okay, I'll finish here quickly. So then just some examples. Order convergence and relatively uniform convergence are all examples of convergence structures on vector lattices. And then also unbounded order convergence and unbounded relatively uniform convergence are also such examples, because you can You can make an unbounded modification of every suitably nice convergent structure on a vector lattice. And I will end here and just show you some references. Thank you.
Thank you very much, Professor van der Walt, for a very enlightening speech. Does anyone have any questions for the speaker? No?
Yes.
Yes, Professor Azuzi, please.
Thank you for this nice talk and interesting topic. It seems here that quasi-subnets are more suitable than subnets. Could say that we don't need the notion of subnets anymore?
Yes. Actually, I mean, quasi-subnets capture everything you need about when you want to talk about subnets. That sort of you have this asymptotic tail behavior being the right thing, and it seems simpler than classical subnets. So I wouldn't say that I can say for certain that you don't need old-fashioned subnets at all, but I think for a lot of things, quasi-subnets turn out to be easier to work with.
Okay, for admissible nets, is all this sequence of Vn of X are needed? All of them in practice?
No. No. Let me just find out. No, you don't actually need all of them. I think you only need go up to n equals 5. I think I think that is enough. See, the problem with admissible nets is that if you start with an admissible net in X and you map it via a function to a net in Y, then it may no longer be admissible in, so the image net may not be admissible in Y. And then even though you can define your convergence structure using only admissible nets, you do need to talk about convergence of non-admissible nets because you want to talk about continuity.
How to manage this problem?
Well, so you will say that if you have X alpha, say, admissible, and if X alpha converges to X and Y beta is tail equivalent to X alpha, then Y beta also converges to X, even though Y beta may not be admissible. So a non-admissible net converges if it is tail equivalent to an admissible net that does converge.
Okay. Just one more question, if you.
Not at all. Please go ahead.
Yes, notion of compactness and.
Yes. So all topological notions that you can express in terms of convergence of either nets or filters can be defined in a convergence structure. So compactness in a convergence space you would define as follows. So a convergence space is compact if every net has a convergent subnet. And likewise, you can define open sets, closed sets, and so on.
Okay, thank you.
Okay, you're welcome.
I have a question. Excuse me.
Yes.
if for the sufficient and the necessarily and sufficient condition for the relatively uniform topology to be topological,
Yes.
means that the space must be with order unit. And what about with if the space has a weak order unit?
No, I don't.
I think that we can weaken this condition for the following, that the relatively uniformly topological is topological if the universally the relatively uniformly complete for the space has a weak order unit.
Oh.
Because if we have the weak order unit, we can work locally. So the space become with strong order unit. I think that is.
If you have, so you have a relatively, so what completion condition do you put on your vector lattice?
The uniformly complete.
Yes, okay, uniformly complete.
I think that is airy, the uniformly complete. If the uniformly complete has a weak order unit, then the space is the relatively uniformly topological is topological. I think.
No, I don't think so. I think C0 would be a counterexample. The same argument that works here for C00 for finitely supported sequences. I think you can. Oh no, wait. This may not work. No. Okay, but I will have to think about this. Thank you.
Thank you.
No, but there is an equivalence in your result, no?
Yeah. Yes.
Yeah.
There is
yes.
For the space C, not for the universally the uniformly complete. For the space C.
Okay, let me think about this.
Well, certainly if you work in the subspace E, where E is the weak order unit, and you look at the E-bounded element, that certainly has a strong order unit in it.
Yes.
So, and that's a generating space for your original space. So surely it would, I think Kazuzi's right. The only way you could have something that fails is if it grows in size very rapidly.
Yeah.
But so anyway.
Yeah.
It's very close to it.
Okay.
Because the area generated by the weak order unit has a strong order unit, so we can work locally and then we can get the results.
No, but then you're only working in a principal ideal in your space and not in the entire space. So you may have relatively uniformly convergent nets that are regulated by things that are outside this ideal, and I think that will cause problems.
In the case of in the uniformly complete of the space.
I don't know.
No, but
thank you.
Okay.
Thank you very much. Sorry, I have to interrupt. We have 1 minute until our